to recall what we have done yesterday. So yesterday we talked a little bit about the model introduction, its application. Then we went through the input data and the basic concepts which are present in the model. Then we saw the model interface, followed with watershed delineation and HRU delineation. So yesterday there was quite a hassle. We could not finish the HRU delineation. So we decided that we would go right from the beginning. Today, we create a project, then we do the watershed delineation and followed by HRU delineation and all the other steps which are required to run the model. So without wasting time, yeah, I would request all of you who wanted to work with me, yeah, we can directly work with the QGIS. So you guys can open your QGIS. Okay. So this is how the QGIS window looks like. If you have a QSWAT installed and plug-in installed, then you would see an icon somewhere here, or you could also see here in this taskbar. So what we do is, in order to start, we need to create a new QSWAT project. So as this window opens up, you click a new project. Okay. I have no idea why it's so. Let's create a new project with today's name. And as soon as it's created, you would see the name which you have given or how you have saved your project. And then the first step for the watershed delineation is activated. As we click here, you could see a new window pops up, and there, as I have explained yesterday, we need certain steps for watershed delineation. There are two important inputs which are required to do the watershed delineation. The first one is digital elevation model, and the other is input outlet information. So without wasting time, we just click here, and then what you have to do, you have to navigate to the folder. I really hope that today you guys have access to the input data. So we navigate to the input data, and then there is a folder named DEM. Click it, and then you need to select a file which has the extension called TIS. And as soon as you do it, it is successfully loaded into the ArcGIS window. Now I would like to show you one. So we also have the information about the stream network into the basin. You could click here and change the type, how it looks, say for instance. So as I have mentioned yesterday, why I have this? As I have mentioned yesterday, we also have an information that we could use a burn-in option to create the stream network. At first, let's try to create stream network without using the burn-in option, and then I will explain why this burn-in option is important. So let's, so here maybe I select, we need to select a threshold for creating the stream network. So let's see, I have selected a threshold of 90 hectare, and then I click onto the create streams, and it would take a while for the model to create the stream. And see here, this blue is the network of stream which is created by the model, and red is the original stream which is provided to us. So there is one information which I wanted to show you here. So see here, the stream which is created by a model is not exactly the way it is provided to us. So therefore, this burn-in option of the stream comes in handy, and it is also advisable to use it. So if the catchment has a lot of anthropogenic impact, or the river has suddenly changed its course, then the digital elevation model is not able to create an exact stream. So that is also this burn-in option becomes really useful. So say for instance, if I use a burn-in option now, and create new stream network, then you see that the last time it was deviating. So now, because I have provided a burn-in option, then it is creating a stream which is representing the better network. So say for instance, so now this inconsistency is corrected. So if we see here, the network which is created by the SWAT model is until here. And if you want to create a refined stream network, then this threshold comes in play. So if I reduce the threshold, then you would see the model is able to create a refined stream network. So here we see that this is great. So now we choose the inlet outlet model outlet. So here we go to the input folder, then we choose a main outlet folder, and here we choose a FHP. And okay, so here you would see. Then we need to check whether it is in the radius where model is able to consider it as an outlet or as a point. So we checked. So it's showing 1, so it's correct, and then we create the watershed. So here in my case, I have no idea why it's taking. So here it's saying that there is already a outlet which is present, and this process which I have done, it's not able to overwrite it. But if I click OK and create it again, it works. So now here in the QGIS window, you see.
Bhumika, sorry to interrupt you, but
Yes.
On your screen or somewhere, I think there are some red lines. Is it possible for you to erase those lines?
Yes.
Yeah, those were creating confusion. Thank you.
Yeah. Thank you for telling this. Yeah. So here the watershed is created. Then we can adjust the created watershed by merging some of the subbasins. So let's see here, we select the small subbasins. So here we have two options how we can merge the subbasins. So one could do it based on the area and also based on the percentage of the mean area. So let's here select area, and then we try to merge all those subbasins that has area of less than 10 hectare. So as soon as I select it, I would see there are some subbasins which are selected by the model, and it shows in the yellow color. And this is the number which is shown here. Save. Then here we would click merge in order to merge those subbasins. And here you would see that there is a warning that pops up that which says that you cannot merge a subbasin which has an outlet. So here, if you remember, it was showing yellow for these two subbasins, and if we merge these two, one of them has an outlet, and if we merge these two, then the overall geometry of the watershed is destroyed, and that's why model is suggesting us not to do it. So we clicked OK, and then it didn't do it. Now we have an option to add a reservoir corresponding to a specific subbasin. So we don't have any information, so I'm not adding it, but I can add the point source to each of the subbasins, and this is advisable if we wanted to do let's say, for instance, nitrate simulation, and we have some water treatment plants present in the subbasin, so it comes very handy. So just add it, and here as you see that the points are shown, and we click OK. So this process of HRU delineation is done, and here and now if the first process is done successfully, then the second window, which is telling us that we could go ahead with the HRU delineation, is activated. So let's go and do the HRU delineation. So here for doing the HRU delineation, we need 3 or 4 important information. One of them is land use map, then soil map. Then we also need the lookup tables for land use and soil map. Then we also need information about the slope. So let's go ahead and do it. So we click to this tab, and here we navigate to the input data folder, and then from there we navigate to the land use, and we select this TIF. And here we need to use the user defined. We have a CSV, so we use CSV option here. Then the same way we'll do for the soil. So soil TIF. And then here in this case, we also select use CSV. So now we have incorporated the land use and soil information into the model. But apart from this, we also need soil physical properties into the database. So what we will do, we have that information already. So here in the input data folder, you have to go to this folder called lookup, and here you have an Excel file named user.xls. And here we have the information about the soil physical properties. So what you have to do, you have to copy this, and then you have to go to the place where you have created your model. Say for instance, today my model is QSWAT 31. So here you need to open this QSWAT reference 2012.mdb. And then here you need to find user soil. And then you need to click to here to go to the bottom. So say for in my case, I have already this soil in copied here, but if you don't have this, then you just have to simply copy and paste it here. So you just use this copy from there and then use this paste command and it works. I hope that this is clear until here. Now we move to further to the HRU delineation, and then if we have already the soil data as the required soil into the soil database, then we go ahead and read it. Before doing that, we need to select the slope. So this is, I don't know, it's visible for you, but this is, we need to here provide the information about the slope classes. So let's say we wanted to have 4 different types of slope classes from 0 to 5. So 3, 0 to 5, 5 to 10, 10 to the rest. And then we need to read the lookup table. So here you have an information. So it is telling us choose land use lookup CSV file. So you have to navigate again to the input data folder, and then you have to navigate to look up. So you click that, and then you have to select robit landuse.csv. Then again, it is asking us to upload the soil lookup.csv. So here you need to select this one, not this one. So soil robit underscore soils.csv, which has a less size. So the purpose of these lookup tables is to connect the maps with the database. So now we have incorporated everything what is required. Then for creating the HRUs, we have an option that how we wanted to do it. So say for instance here, if I choose the first one, so here if I hover down, it says select to create one HRU in each subbasin formed from the land use, soil, and slope band with the largest area. If I wanted to choose this, then it would only create one HRU for one subbasin. We don't need that. More or less the similar behavior is observed here. If I would choose a dominant HRU, it would also create one HRU per one subbasin, but corresponding to the area of the corresponding to the potential HRU that has the maximum area. Then we have an option that we could filter the land use by slope, soil, land use, slope, and soil. And here, for selecting the threshold, we also have an option. We could select based on the percentage of subbasin or based on the area as well. Say for instance, here, let's select this filter by land use, slope, and soil and slope. And here, let's say that the area of, so say for instance here, what does it refers to? It refers to that if a subbasin has a specific land use less than 5%, that it would merge it to the nearby. So here I'm choosing 5% and then go. here as well 5, and in case of slope I wanted to choose 10. So you could choose it based on how refined you want your HRU to be. Then so here there is a button which says create HRU. We could do it, but before doing that, I wanted to show you one thing where I wanted to use the split land use option. So if I wanted to click this split land use option, then I have an option of splitting a specific land use into different types, say for instance. So say for instance, at present, I have 3 different land use: agricultural, pasture, and forest. So say I wanted to convert for agricultural land use into corn and summer wheat. So here I could choose that crop, corn. And as soon as I click it, so here it shows. So this is the land use, and this is the information what I wanted to convert this land use to. And here it is showing the percentage, what percentage of the agricultural land use I want to be converted into corn. At present, it is showing 100%, but I don't want to convert it into 100%. I wanted to convert agricultural land use to corn and some spring wheat 50-50. So I would add another land use which is corresponding to spring wheat here. And then I would change the percentage. Then I would save edits and save split. Then we also have an option to exempt certain land use from splitting. So if you click this, then here you see I have already splitted the AGRL to corn and spring wheat. That's why we are also seeing these 2 options for the land use. And here, if you wanted to say, for instance, exempt forest, then you could click this and okay. But at present, we don't want to do it. But I just wanted to show that this is also an option. And then here you could click OK to create. So this is done. So here you see it is providing us the information that we have 38 subbasins in this catchment, and corresponding to the information which we put to create the HRU delineation, it has delineated 292 HRUs at the end. So I hope that it's clear until now. Then we move to step 3, where we would be putting the weather data. And before, so as soon as we click it, a new window of SWAT editor pops up, and we need to connect it to the databases. And here we could go ahead with incorporating the weather information and further on writing the SWAT input table. And before doing this, I would like to provide you some more information. So this I have already provided you the information that you could, so instead of, the information which I provided is like you could go to this this database, which is present in the folder where you have created the model. But if you don't want to do it every time, what you could do is you could directly go to SWAT, go to SWAT editor, and click on to the databases, and there you would also find this QSWAT reference 2012 database, and you could also copy your user soil there. So if you would do this, then you don't have to copy it every time when you create a new model, model will directly copy it for you. So here, what I wanted to give you more information. So we have 5 different weather data which is provided to us. So the format, the precipitation in terms of millimeter, solar radiation model requires in the form of megajoule per meter square. Then we also need the information about maximum and minimum temperature that should be provided to us in degrees Celsius. Then wind speed should be in meter per second, and relative humidity should be in percentage. So if you would open your so if you go to the folder which is provided to you and to the input data, and here if you would open this climate robot, you would see a lot of information. So it has these files which is providing us the information about the station, and then these files have the information about the data. So say for instance, so if I would just quickly open it, so this file looks like this, and this is corresponding to the file for the temperature, and this should be the format. So it should be it starts with the ID. You have to give the name, and this name should be same name where data is provided. So say for instance here, so model read. So we only have to input this file into the model. So model reads it, and then it searches this file into the folder and then creates the database. And then how this temperature file should look like. So it should, so here at the header, we have to provide the date, and it should be first year, then month, and then days. And for in case of temperature, we have to provide maximum and minimum temperature. So the first value is corresponding to the maximum temperature, and the second is corresponds to minimum temperature. Then I would go back to my presentation. So I have already mentioned this. Then so now I would define how the weather data should look like. So I have already explained this by using the temperature station file, but if you would open the relative humidity station, it would look like this. But what in case if we have a lot of stations, not a single station? So here, if you have a lot of stations, the file should look like this. And these, say for instance, in case of precipitation, we have 1, 2, 3, 4 stations, and the name of the file which has the precipitation data should be same here. So say for instance, if you would open a precipitation data, it would look like this. And then so I have already mentioned this, that the format should be year, then month, and then days. And if there is a missing data present, then you have to define it like this, minus 99.30. And one more information which I would like to share with you, that in case of SWAT, if you would put if the data has more than 3 decimal, then the model shows error. So just keep this in mind. Then yeah, I have explained this, that we have to connect it every time. Then let's go back to the model itself and do. So this is connected. Then we input the weather stations. So here we need to choose the WGEN underscore user, and then we can navigate to the folder where our data is. And for the rain gauges, we have the observed data. That's why we are choosing rain gauging. the engages, and here we also have the daily information about the data. So we go here, and then we navigate to the folder where you have placed your data. So input data and then Climate Robert, and here so it's telling us which gauge I had to import. So import precipitation gauges. So this PCP Rob station I have to import here. Then I would go to import temperature data. So climate stations, not the simulation. So this is TMP Rob station that has the information about all the stations corresponding to temperature. Then we do the same for all the stations. Relative humidity, solar radiation gauges, then so try to put those, if you have created somehow the name of the station with not station, then try to look for the size. So these the files which you are uploading here should have a really less size. And then we click OK. It would create the database corresponding to all the weather parameters, and then we click OK, and then cancel. Now our weather is incorporated into the model, and then we will go to write input tables. So why this is necessary? I will quickly show you. So this is the folder where my model is, and if I choose scenarios, go to default and text in, text out. So here is the location where all the files which are created by the model is stored. If I wanted to, so if somebody wants to look into the output data, output simulated by the model, then one has to navigate it to whatsoever full model name he or she has. Then he or she has to navigate it to the scenarios, go to default and text in out at this present case. So here we see that we only have the files which is created corresponding to the WGN, and then we have files corresponding to the weather variable. So there is no other file. So that's why we wanted to write these. So we select all and then create table. So here it is saying that we use weather database to calculate heat units to maturity, but then this only does best for the US catchments. Here in our case, it's not located in US, so we will just click no. And here it is saying that do we wanted to rewrite the existing point source information? We have incorporated the point source into the model, then click OK. Then this we have not provided any inlet into the model. We could just quickly say no, and we have not also provided the reservoir information, so no. And then as soon as one of the model is writing the files, you could see it here at the bottom, and also the red becomes green and you completed is there. So wait for a little bit to so now it's done. So we cancel it, and so now all the things are done. So there is one more thing which there is one more tab called database update. If we change any of the database, then one could go to this database update and then select and then update database. We have not done it, so I'm not doing it. Then I would talk about this in a while. So let's go back to the text in, text out and see. So here you see now we have quite a lot of files. I want to see how many of them. It's not showing, but let's see. So corresponding to one HRU. So this is this is the GIS code, and this here, this one is corresponding to the subbasin, and the last number corresponds to the number of HRU. So this is telling us the information that this is first HRU of subbasin 1, and corresponding to one HRU, we would have these many files: 1, 2, 3, 4, 5, 6, 7. So corresponding to one HRU, we have 7 files. And you see, previously there were really less number of files, and now when we write all those, when we write the tables, then we have around 2,000 items in this text in out folder. So the idea behind merging the subbasins or merging some of the HRUs was to reduce these number of files so that we would the model is computationally efficient. And then we could just run the model. I have explained this to yesterday, but I could quickly go again. So here we need to provide the start and ending date for the model. Then we need to provide the which SWAT executable we wanted to use. So this 64-bit release, this is faster. Then the model anyways runs on a daily basis, but we have an information, but we have an option to print the outputs in terms of daily, yearly, or monthly. Let's check yearly. That would be faster. Then here we can also have we could also provide the information to the model that how many years model would skip it or consider it as a warm-up period. So let's select 5 years. So model runs for those 5 years, but it will not print the output corresponding to those 5 years. Then if we need any other output apart from what model is printing, we could just click to all those present here. Then we have an option like how we want our output files to be. Should it contain all the variables or minimum variables, or we have an option for the user defined. So these are the 3 main output files which are mostly used for the water balance analysis. So one is the output.reach, output.subbasin, and output.HRU. I would explain this once we run the model again. So here, if a user doesn't want to write all of them, then he or she could just select whatever parameter he or she wanted and then just runs the model. So say for instance, here I would need these parameters, and I don't need 3. And then here in this case, I wanted to have ET, sedimentary water use, groundwater. And in HRU file, I wanted to have copy. And then I would click OK. And then you could set up your model. Setting up your model is required because if you are changing anything here and you are directly running your model, then a model will use the previous settings. So whenever you wanted to change something here, then you have to click setup and then run the model. So it would run for all the years. So now run is successful. We could cancel it. And then so we could import certain outputs, and then we could save it, say for instance base model, and then so if you wanted to see it where it is saved, you have to go to scenarios, and then here, so default is the one where if we change anything, everything model runs everything in the default folder. But if you wanted to save your previous simulation or the base model, you save it the way I have shown you. And then say for instance, after some, so like now you wanted to calibrate the model, or you wanted to incorporate management scenarios into the model. Somehow your default model corrupts. So what you could do is you could simply replace your base model with the default model, and then you would have the original version of your model with you. So this comes in handy. Then maybe it would be good to take a 5-minute break, and then I would show you how to modify and what are the files and what are the outputs. Let's exit this, and I will stop share.
Thousand kilometers square. Hello.
Yeah, we are listening you, Tati. Go ahead.
Yes, but in 2000 kilometers square, the only two soil it shows it a big problem, I think, because our result is not appropriate, because the
Yes,
R
I
is
would.
0.1 something.
I would recommend you again to go back to that database that I just shared from SWAT website that Dr. Balaji and his team has created. You might can get more soil values in there. 2 soil values just for 2000 square kilometer. I think it's very coarse. You won't get realistic information.
Okay, thank you. Okay, I'm done.
Hello, sir. Hello, ma'am.
Go ahead.
I'm Siddiq Muhammad. I have problem in digital elevation model because my area is so big. So I download 70 pieces of digital elevation model. And when I mosaic it together, the size is became 2.5 gigabyte. So I'm not able to use it in SWAT. I use USGS website.
But then in that case, you can reduce the resolution. So if it is 30 meter, you could make it 1 kilometer, and then the size would reduce. So number of grids would reduce, and then you could see it's a trial and error, and you see. So like in my case, I was also working with 29,000 kilometer square area. And when I was using 30-meter grid, it was not working. So I resampled it to 1 kilometer resolution, and then it worked.
How can I resize it?
So you could do it with the QGIS or ArcGIS. You just have to use the resample.
So there are a lot of tutorials, Mr.
Yeah.
Siddiqui, on YouTube that you can see. Means we are really apologetic that that is out of the scope of this workshop, but there
Yeah.
are a lot of YouTube videos and tutorials that you will find how to resample your digital elevation model.
Yeah, I already checked, but it's not
So it's
available.
just
Okay.
you have to go to the catalog, and then it's just one step. So you would
Okay.
find it in Google. It's really
Okay. Okay. Thank you.
Pooja, we did not understand your question. What do you mean by SWAT can account? So SWAT can handle any size, but again, as I'm mentioning, so you have to be very wise with for what research questions are you using SWAT for. So like where somebody just mentioned they are developing River Krishna model, and they're dividing into 3 different basins. So that is a wise decision, I would say. You can have the entire India in one SWAT watershed, but does it make sense to have one watershed or have multiple watersheds? So area is not a limit. The problem with SWAT comes in when you are developing a model less than 20 hectares. So that is where SWAT start creating problem, the field size scale. So SWAT is a watershed model. You cannot have it, means you can, but it all depends upon how you parameterize your model for setting SWAT for field scale studies. I hope that answers your question. Bhumika, you want to start your presentation? I can start answering questions on the chat.
yeah. Okay, thank you. So I think I'm audible. So now I would talk a little bit about the basics of heat unit concept. I have covered it yesterday, but I would give it a little bit brush up, so that because this we would be using it for, I would explain this, or I would use a heat unit concept to incorporate one crop type. Then I would also show you how specific parameters can be modified into the model, and then we incorporate the management operations into the model. So as I have explained yesterday, heat units are accumulated whenever the air temperature exceeds the base temperature. So say for instance, if you see a figure here, so this red thing shows the variation or the values of mean daily temperature, and this blue line shows the base temperature. So for each degree above base temperature, one heat unit is accumulated. So say for instance, here 8 degree is the base temperature. And then if I have an average temperature of 20 degrees Celsius, then on that day, crop accumulates 12 heat units. So the crop grows based on, in the model, based on this concept. So it accumulates the heat units, and based on the heat units, leaf area index, and then the biomass is calculated. So here, so the model uses potential heat units. So potential heat units are the total number of heat units which are required for a plant to reach maturity. And this is calculated by the heat units, which I have shown you. So the average temperature minus base temperature, and that is accumulated over the days which are required to achieve maturity. Say for instance, here, if you see in this table, if there an example is given. So from so if we wanted to calculate the heat units, so heat units are calculated. There are 2 types of heat units. One is the heat unit corresponding to the base T0 temperature, and the other is plant accumulated heat units, in which we use the base temperature corresponding to that specific crop. So here in the model, so say for instance, if I wanted to implement tillage and other operations, then the model uses the heat units, which is corresponding to the base zero temperature. But once the crop is planted, then we use the potential heat units, which is corresponding to the plant. That is, here we are calculating it corresponding to the base temperature of that specific crop. Say for instance, here you see, so this is the accumulated heat units on 24th of April, corresponding to the temperature T is equal to 0 degrees Celsius, and 4050 is the total heat units occurring on that year. So if I wanted to calculate the fraction of potential heat units corresponding to T is equal to 0, then what you do, you use this value and divide it with 4050, then this number comes. So as I have already mentioned, that if we wanted to implement tillage operations, fertilizer, whatever is applied, whatever management operations we are doing before the crop is planting, we have to use the fraction of heat units where we are using temperature is equal to 0. Once the crop is planted, then we have to use the potential heat units corresponding to the base temperature of that specific crop. So that's why here you see, if I wanted to implement these operations, then at first I would use the heat units corresponding to T is equal to 0, to these. And then here in my case, so the crop is planted. And once the crop is planted, you see it should increase, but here I'm using different type of heat units, which is corresponding to the crop, and that's all. So I hope that this is clear. If it is not, then just let me know. I will try to explain it again. So then how actual plant is growing or actual crop yield is calculated into the model. So here the plant growth factor quantifies the fraction of potential growth achieved on a given day, and that is calculated by 1 minus maximum of 4 different stresses, which plant is having. So say for instance, plant could have water stress, temperature stress, nitrate stress, and phosphorus stress. So we calculate this parameter, and then this parameter is multiplied with the biomass that has occurred on that specific day. And if we wanted to calculate the leaf area index here, I don't know you guys could see it or not, but then so here it's leaf area index, and then the change in leaf area index on that particular day multiplied by this parameter would be adjusted corresponding to the plant stress. So the actual biomass and actual leaf area index is adjusted corresponding to these 4 stresses, which is occurring in the plant. Then I would like to show you how we could edit certain variables into the SWAT model. So I would show you the variables that we would change so parameters, sorry, not variables, parameters that are corresponding to sub-basin data and corresponding to watershed data. One important thing which I wanted to mention is, if you change anything and if you wanted to see that change into your model, then rewriting the SWAT input files is required. So now I would go to the model and explain. So in order to see the parameters, I need to go to edit input and run SWAT. Then I have to connect to the database again. Then here I could go to edit SWAT inputs. So there are a lot of things which we can edit into the model. Say, for instance, let's see the databases. So here we have a lot of databases that are already present into the model. Say, for instance, for soil, we have incorporated the data, the soil data, which is corresponding to this watershed. So let's open this. So we click this and then click OK. A window would open. Yeah. So a window would open that has information about on the left hand side. It has the information about all the soils. And then, so as soon as we select this soil, we could see information, soil information here. So it's providing us the soil name, number of layers, hydrograph, and maximum rooting depth. And then see here, the number of layers are 3. And we could also see here the soil information corresponding to 3 different layers. If you wanted to change anything, you could change something here, and then you have to save those edits, and then you have to rewrite the files. If somebody wants to change something into the soil database, it is not advisable to do it from here. Either you could do it from .mdb file, which I have shown you before, or there is another way to change a certain soil parameter. I would explain that in a while. Then here you could open the land use, land cover, or plant growth database. Here, say for instance, I wanted to see the parameters corresponding to corn. Here, so if I would hover it, you would also get an information and maximum minimum value of that particular parameter. For more information, you could go to this SWAT input output documentation, and here you would have more information about the specific soil parameters, specific plant parameter. Say for instance, let's see HVSTI. Try to see it. So you can just HVSTI. And here you could see information about what this parameter is and how this value, what this value signifies. So you could read more. Then if you wanted to change anything, you change that specific parameter and save edits. And once you save the edits, you have to go, I will tell you, to rewrite. Say for instance, now we have a fertilizer database, so there are already a lot of fertilizer which are present, but if you wanted to incorporate your own specific fertilizer, then that can also be done. So you could add new, and then you could define the name and all of the parameters corresponding to that fertilizer database. More or less the same thing is there in case of pesticides, tillage, and yeah. Then we have here the other tab is corresponding to point source discharges. Here, as I have added one point source corresponding to each sub-basin. So here you could, if you wanted to add information, so here that can be done. So currently it's not editable. You have to go to edit values, and then here you could provide the data. So if you wanted to provide a constant data, if you wanted to provide annual data, monthly records, and so there is also an option if you wanted to upload the average annual daily loading. And here it would be equal to the number of subbasins we have. But if you don't want to do it from here, you could go to your model, text in, text out, and here you could also see. So this is, and here you could provide the information of the point sources which you wanted to incorporate into your model. So then inlet discharges, it would say that we don't have any inlet discharges. That's why we cannot see it. Then for reservoir, it would give us the same message because there is no information on reservoir that is incorporated with the watershed. If you would incorporate any reservoir corresponding to a sub-basin, then this window will pop up and then you could provide some data corresponding to that. So now we go to the sub-basin data, and here a new window pops up. So here we have a lot of other tables or a lot of information where you could change parameters. Say for instance, for soil, this would provide more or less the same information that I have shown you in the soil database there. And so the soil is corresponding to the HRU. Therefore, at first we need to select the sub-basin, then land use, then soil, and slope. Here, if you click OK, a new window will pop up, and here you would, if you need to change anything, you need to go to edit, and then here you have the information of this particular soil, and then it say for instance it has 3 layers, and then here 3 layers. If you wanted to change anything here, say for instance I wanted to change this bulk density to 1.25, then you need to go to extend edits, and if you only wanted to change it to this specific subbase, this specific HRU, then you need to select just one, and this HRU is corresponding to subbasin 1, land use corn, then soil, and then slope is 0 to. But we usually don't use this for just changing it for one HRU, but that can be, you could just save edits here, so that would done. But this function comes handy if I wanted to change all subbasins for corn crop, for all the soils, and for all the slopes. So this bulk density would be changed from 1.22 to 1.25 for the combination that I have chosen, and then you have to do save edits. I'm not doing it, I just want to show you. Then we have, okay, this we don't change, so we go to the sub-basin, and here we have a lot of parameters corresponding to different sub-basins. So here, if we are, so this is providing us the area, latitude and longitude, then the sub-basin elevation, then we have P-labs, T-labs. So these are the parameters which we would be using if the catchment is dominated by snow. Then we have a lot of other parameters. So I know that it's a little bit overwhelming, but you could go to this input-output documentation and type what the name of the parameter, say for instance CHK1, so it's here, CHK1, so it gives the information about the effective hydraulic conductivity in the tributary channel LUVM. So you could get all the information from that input-output documentation, and the same is here. If you wanted to change any of the parameter, you change it there, and then you save the edit. You go to the extend edits if you wanted to extend that same parameter to other. Say for instance, so our model is running for 1990 to 2014, and during that period we don't have this concentration of carbon dioxide. It was around 390, say for instance. Then and I want this parameter to be changed for all the subbasins. So I would click this extend edits to selected subbasins. I would click all and then save it. And once I do this, I have to go to here to rewrite these SWAT inputs. So it was subbasin, and then I have to write. So now the change what I have done is written into the text file. So The thing is this, whatever we do here, as soon as the model is not having this change here in this in these text file, model is not responding corresponding to that change. I would show you one example. Say for instance here, we go to sub-basin data again, and then groundwater, and groundwater parameters are also corresponding to HRU. So let's change this recharge deep to 0.5. So I wanted to change it for all and then save it. So previous value was 0.05 and now I have changed it to 0.5 just to show you. Save edits. So now I have saved the edits, but I have not done rewrite SWAT inputs. And let's go and open any of the groundwater file. So this is the groundwater file corresponding to 6 sub-basin, and in 6 sub-basin, this is the number corresponding to the HRE, 4 HRE. So if you wanted to see, so we have changed the recharge deep there into the model, and here it's not changed. So I have changed it to 0.5, but the default value of this recharge deep aquifer percolation fraction was 0.05. So I close this and then I go to my model and then I rewrite it. So I go to the groundwater file and rewrite it. And then I open it again and you see it's changed. So that's why I'm putting so much emphasis on whenever you change anything into the model via using your data model graphical user interface, then you have to rewrite it. Only then it would be reflected here. And if it is not reflected here, model will not use it, because model takes the information from the text files which are created in the text in output. Now let's go back to the model. So apart from so now let's check the management options. So here it is providing us that is there any initial plan or was there anything initially growing into that field. Then we have a general management parameters. Then it is also providing us the information about the irrigation management and all. But the most important part for us, if we wanted to incorporate any operations into the model, is this. So here we could, as I have already shown, that we could use heat units to implement the management operations, and also we could use the dates for incorporating the management operations. So here I would like to show you how to incorporate management operations into the SWAT using dates and also for heat units. So we choose these dates. So I would change, okay, this is wrong. I would change corn to, so I would implement tillage, fertilizer, planting, auto irrigation, auto fertilization, and harvesting to corn based on the dates. And then for pasture, I would in pasture land use, I would grow alfalfa there, and I would use these heat units to incorporate these management operations. So say for instance, I just wanted to write. So now let's go to the model. So if you wanted to delete anything, you delete by using this. And if you wanted to edit it, you select it and go to edit operation. So here, the plant ID corn is already selected. And for corn, I wanted to schedule it by using date. So here it's saying, yeah, we need to select it, yes. And then here I can select on which month the crop is growing. Say for instance, here I wanted to grow it in April 20th. So I could just type it 20th April. And then, so in case of heat units, we can calculate it based upon the crop window, and as I have already shown you. So this is the default value which is used by the model, but for each watershed this value is different. So one has to calculate it based upon when the crop is growing and when crop is harvesting. So you pick the annual average temperature and then use the base temperature corresponding to that crops and calculate the potential heat units. So here I'm not changing it, but one need to change it because this is the default value and sometimes it doesn't work. So here I would click OK. So here you see on first year, on month 4 and day 20, my crop is growing. But before that, in actual practice, we just directly don't grow crop. First we till the field, then we apply fertilizer, and then we plant the seeds. So if I wanted to add other operations, I would go to add, and here I have a list of a lot of operations that I could implement into my model. So say for instance, I wanted to implement tillage. Okay. And here I wanted to do tillage before. So say for instance, April 15, I want to till my crop, and here I have an option that I could use different type of different ways by which, so let's say I wanted to use cultivator. Okay. Then I wanted to, so because it was before, it is added, so based on the date, this operation I have implemented before, so that's why it is added before. Then I wanted to add fertilizer application. So I wanted to apply certain fertilizer on 16th of April, and then here we could choose a list from the list. Let's urea, and this is the amount of fertilizer that is applied to this specific HRU. And let's see that I wanted to apply 50 kg, and then this is the amount of the fraction of fertilizer which is applied on the topsoil. So let's say out of total 10% of this fertilizer or 20% of this fertilizer is applied onto the surface. You could get these values. So these values should be local, taken from the literature of the area which you wanted to model. So let's see this. Then so this operation is only applying fertilizer on this particular day. What if we wanted to apply fertilizer based on when plant needs it? So in that case, I would add another operation here, which is showing auto fertilization. So here it would add fertilizer whenever plant is needing it. So let's add urea again. So here this is the nitrogen stress factor of cover plant that triggers fertilizer. So this value ranges from 0 to 1. So whenever the threshold goes less than the value defined, then model applies irrigation. So say for instance, here I wanted to put 0.75, then this is the amount of fertilizer that is applied on one single dose when there is a stress. So let's say I wanted to apply 50, and then this is the total maximum amount of fertilizer that can be applied on a given HRU. So say this is 250, then this shows the efficiency of the system which is applying irrigation fertilizer, and then here it's like how much amount of fertilizer which is applied on the topsoil. So let's say 0.1% of the total fertilizer or 0.2% of the total fertilizer. So you need to check these values. Okay, see, edit, it was wrong. I need to select the month, April, and I wanted to add it after I'm planting the crops. So let's say, for instance, I wanted to start from 25. So it's added later. Then my crop also needs irrigation. So let's apply irrigation as well. And I wanted to apply irrigation also later once the crop is planted. So April, then 26. So here in case of so like for providing the irrigation based on the demand, we have two options. Either we could apply irrigation based on the plant water demand, so like how plant is needing it, or we could apply irrigation on the basis of soil water content. Usually on the real practice, farmers apply irrigation based on the soil water content, but here I would just show you based on the plant water demand. So here that's the threshold that triggers irrigation. So say for instance 0.8, whenever this threshold goes less than 0.8, and then model triggers irrigation. So here this is the irrigation efficiency of the system. If say for instance I'm applying water by using the pivot irrigation system or by using say for instance sprinkler, then the irrigation efficiency is 0.75. If I'm using pivot or I'm using drip irrigation, then the efficiency changes accordingly. So this is irrigation underscore mix is the amount of irrigation that is provided when this threshold is triggered. So let's say 20. So whenever a plant needs water, a model applies 20 millimeter of the water. Then here it shows how much amount of total water is lost as a surface runoff. So let's see, 0.1% of, so 10% of the total water which is applied to the plant, it is lost as a surface runoff. Then here we could also provide the information from which source we wanted to take water. So say for instance, here if you would hover it, we could see that if there is no irrigation, 0. If I wanted to take water from the reach, it's 1, reservoir 2, and thereon. So let's see, I want to take the water from the reach, which is flowing into that sub-basin. So this is sub-basin 1, and this is reach. So, and here this is the irrigation source location. So if I would choose 1 here, then I need to give here the sub-basin number. So here in this case, sub-basin number is 1, and then okay. So now I have done tillage, I have applied fertilizer, then I have grown my crop, then I have applied auto irrigation, auto fertilization into the model, then I would harvest my crop. So harvest and kill. So I would use harvest and kill. I wanted to harvest my crop in September. So and then okay. So now all the operations are incorporated into the model. Then I wanted to extend it. So I wanted to select it to the selected HRUs, and here I wanted to click this as well, extend management operations. I wanted to convert all the corn management operations to the one which I have shown you here. So all soil, and I would save the edits. So by doing this, all the corn which are present in any other subbasin, they have this management operations incorporated. So let's check quickly. Previously it was subbasin 1, and now I wanted to check for subbasin 7. So operations here. There is one thing which I wanted to show you here is in case of auto irrigation. See here, the source is one which is reach, but here in this HRU, it is still taking water from subbasin 1. So that has to be changed. I would show you how to change it there from the .mdb database. So now we have incorporated the management operations corresponding to corn. So let's implement alpha, and here I would use heat units. Pasture. Then delete the operation, and then here I can, sorry, I've edited. So in case of pasture, I wanted to use alpha. So that's, as I have already told you, that we need to check these heat units corresponding to our area of interest based upon the average temperature and the base temperature. So just keep this thing into your mind, and let's see how I'm operating. So for tillage, it's 0.1. So let's maybe I would apply right from the beginning. So at first I wanted to apply tillage last in the year, and then here it is. Then if you wanted to, choose let's see, chisel plow. So then I wanted to apply fertilizer application into the model. So here let's see elemental nitrogen. Then here we also need to give the amount, let's try 50 kg, and then here we need to tell how much percentage of the total fertilizer that we are applying goes to the top 10% of the soil, top 10 mm of the soil. And then let's plant. So planting, and then I wanted to plant when the heat units goes to 0.2, and then here I wanted to plant alpha here. So I have already mentioned that these heat units should be checked corresponding to the area where we are growing the crop. Then so let's just do auto irrigation here, and then we could just use more or less the same values. So this is corresponding to the stress, then what is the efficiency of the system, then how much amount of water is applied on every time when the irrigation is triggered, then here how much amount of water is going out as a surface runoff, then source. Say for instance, here I wanted to choose another source, say for instance shallow aquifer. So I wanted to take water from shallow aquifer, and here as well, if I would choose irrigation, then here as well I wanted to give the information about the subbasin. So here it's subbasin 1. Okay, then the last operation would be harvest and kill. So I can just do the harvest and kill, and here it's 1.16. So something what I wanted to show you here additionally. So the more the alpha would grow until the heat units are reached from 0 to 1578 in this case. And when these heat units are reached to that particular value, then this heat units would be 1, but we don't harvest it at the time when it reaches the heat unit. So that's why for the harvesting, we chose heat units greater than 1, so that the crop stays there into the field, and after some days we harvest it. Then you select it, then pasture, sorry, and then we save it. So now we have incorporated management operations corresponding to corn and corresponding to pasture. We close this. And then what I was telling you guys, that we need to change the irrigation source. So sorry, I'll go to, so this is the model database. This is the name of my model which I developed today, and this is the name of the database. If I would open this MDB, and here if I go to MGT2 file, so this provides the information about all the management operations that I have incorporated into the model, or which was from before. Say for instance, for pasture, I chose the heat units this. And then for, so here the management operation 10 is corresponding to automatic irrigation, and here, so this was the parameter irrigation NOA for which I wanted to provide this sub-basin number, and here at present it's 1 because that was defined. So what can be done here is you could copy the sub-basin number from here and paste it here. So now we have the water taken from a specific reach of that specific sub-basin. And then we save it. And then we go to rewrite. And when we do change in management files, then sometimes if I just rerun the management file, it doesn't work. So it is advisable to just select all and rewrite all the files. So let's see. File. So now here I want to see what changes I have done in the .mdb. Are they reflected? They are reflecting here as well. So I'll just go to the operations, then automatic irrigation. Ready, then see here it's the 5 sub-basin and The source is also 5. So whatever we wanted to achieve, our purpose is solved. Then, so now you could also run the model again because we have incorporated the management scenarios. Just select all. Yeah, instead of just select all, we do the setup and then we run. So we can cancel it and we can read the output. So import it to the database and then I can save it. GT. Then save selection. So now there are only two things which three things which are left for this lecture, talking about the outputs, then output visualization, and then SWAT check. So let's, if you guys want, I could just stop for a quick break and then I would cover these three, or if you are really motivated and not sleeping, then I could just go ahead. Any recommendations?
Bhumika, I think we are left with just 15 minutes. It should be.
Okay.
Yeah.
Okay. Then I would just quickly. Let's go to. So this provides. So this SWAT check. It provides the information about how the basic hydrology of how basic hydrology, sediment, and other components are simulated, and it provides us the information that what could be improved. Say for instance, here if I wanted to do the SWAT check on any of the on any of my model, then what I have to do is I would just have to navigate it to the text in out folder of that specific SWAT model. So here I just wanted to see it for the default. So what I do is I would just click the examine model. It would take some time, and here on the right, it would give me the information like for how long the model was ran, what was the number of warm-up periods, how many HRUs, sub-basins, and all those information. And here you could see that it is giving me the warning that I have to examine the hydrology, sediment, nitrate, and all those things. So this provides us a guideline to do to modify the model somehow. Say for instance, in case of hydrology, if I would click into this tab, it would give me the overall water balance. So how much amount of precipitation was occurring for all those 24 years, then evapotranspiration and all those things. Then here it is giving me certain warnings that surface runoff ratio is higher than 0.8, then groundwater is low, and based upon these information, I could just change certain parameters so that my overall hydrology of the catchment is represented. Here, in case of sediment, it is also giving me some information that the overall catchment average sediment yield is 10 metric ton per hectare, which is like really high for this size of the basin. And then it is also providing me the information that corresponding to which HRU I have the highest amount of sediment occurring. So I could just implement, I could just go back to that HRU and try to see what's wrong, or I could just implement the management operations there. And more or less, you could see the same information here that how much amount of inorganic fertilizer is incorporated, how much is the mineralization occurring. This is the information, and here we have one warning that the nitrate is being removed from the soil profile and the simulation ends with less. So we need to apply more. That's what it is saying. And then in case of phosphorus and in case of plant growth, it is providing us. So here I have only so we have winter wheat left, for which the management operations has not been taken care of. And if we see here, we have a water stress days, which is quite high, and plant also has nitrogen stress. So based upon this information, we could work on the model to improve the stress so that we would have good yield at the end. Then here it's providing, so this is important what I wanted to show. So here we have all the crops which is growing, and then we have the information about how much amount of percolation, evapotranspiration, and then this is also giving the yield at the end. So say for instance for this, so this is pasture, so it's not at all growing, so we need to go back and check it. And for I think the last one, it is also not given. So summer wheat, because we have not incorporated the scenario, the management operation, so it's not given the yield. So this gives an information that we need to go back to the model and correct. Now I would like to quickly show you the output files. So for checking the output files, we have to go to the scenarios, default, or any other, and then you can simply type. So we have three main outputs, as I have explained: output.hru that has the information of a lot of parameters corresponding to variables corresponding to HRU. Then we have output.std, then we have output.subbasin, and then there is one more file which is called whatout.dat, and this file gives, I will quickly open all of them and show. So here, this file gives the information, because I have ran model on yearly basis. So here you could see years, and then here it is giving us the information about flow, sediment, and all other parameters corresponding to the watershed outlet. And if we run the model daily, then this file gives us the daily information, and that could also be used for model calibration. Then other file. So this is the most important file, output.std. Oh. Here. So here it gives the information that how many years the model has been ran, what is this watershed area, and then initially, because we have given 5 years of warm-up period, that's why the model is running, but it is not providing us the information. So here 1, 2, 3, 4, 5. So the first 5 years model is not providing any input. But here from the 6th year, model is providing an input because the model is run on a yearly basis. That's why we have the yearly input. If you would run the model on daily basis, you would have daily output here. Then we go down. So once the whole is done, then here, because we have applied irrigation, so corresponding to each HRU, it is providing us the information that how many application has been provided and what is the total average value of the irrigation that is applied on that specific HRU. Then after that, it is providing us the information about the yield and biomass occurring on a specific HRU. Then here we have the information about corresponding to the HRU, their area, how much irrigation is applied, and so yeah, these are the parameters, and this is the annual average values for the HRU. Then we also have the information about average monthly basin values for the entire year for the different water balance component. And then here at the end, we have, this is the same information which we have seen in the SWAT check. Then this is also the same information, hydrology information, which I have shown you in the SWAT check. Here you could also see that how much should be the evapotranspiration, how much percentage of it should be, and then one could do the soft calibration corresponding to that if you have certain information about your catchment. Then here we have the information about the nutrients, phosphorus, that's all. Then I would quickly open output.reach. So output.reach provides the information corresponding to every reach. So here the model is, yeah, this is a very difficult format, but here I could show you. So this is reach 1, and then here is the model which is ran on a daily basis, and then here you see this is the area, and then one could get flow in, flow out, and all the other parameters which I have shown you into the model. That here in this case I have selected all. That's why we have all the parameter. Model has run all the variables. So here if we see it's corresponding to the 38 reaches, and then we have 1995 is ended, and then it's starting from reach 1 corresponding to the next year. And more or less the similar scenario is here. We have so previous file, in that we have all the variables corresponding to the reach, and here we have all the variables corresponding to the subbasins, and you could read more about these variables and parameters from the SWAT input output documentation. Then there is one last thing that I wanted to show you. So this QSWAT has a really good interface where we would directly we could directly visualize our results. So say for instance, here I have saved base model management and default. So yeah, you could, let's select base model, and then I would show you how we could see visualize the model results. Yeah. So say for instance, I just wanted to visualize results for 2000 to 2010. And then here I wanted to see which parameters, which variables corresponding to reach I wanted to see. So say for instance, outflow, flow out, and then what I wanted to do. So like say for instance, I want annual means, and then you just add it. Then let's add one more variable. So say for instance, sediment out. Then I also need the annual means, and then I would add it. Then so you select it here, and then here you need to change the name of the shape file, and then create it. If you would create it, you would see here a map which is created, and here we see that the overall variation of annual mean flow varies from 0.007 to 0.046. It's in centimeters. So that's why this value is like this. And here we could see that as we are moving towards the outlet, the total quantity is increasing. Then if you wanted to see it for the sediment, then we can create more or less the same thing for the sediment, and here you could see. Then the coolest part here is we can directly print a map. So I select here, you select the number of maps you wanted to print. So say, if for instance, if I have more number of variables here, I could just increase here and then print it. So here you could see that we have our map printed. Then we could do a lot more to modify or to beautify these maps. And if we wanted to change anything here, say for instance, if I wanted to change the name of this, then I could just write here, and then I would just change here flow means, and then first you have to select this, and then you select this, and then here. Okay, I think I did wrong. Yeah, this is flow. And then I have to select this, and then so this is sediment. And then you could also change this as well. So for instance, SWAT results reach. And once it is done, you're satisfied with the map, you could just export it as PDF or any other format which you like. Then more or less similar, we could do it for subbasin. I would just quickly show it here. Say for instance, if I put transpiration, I would add it, annual means. Then we have sediment yield. Then I would also add it here. And just don't forget to change the name here, subbasin ET, and then create it. So like if I would not change the name, the previous file is overwritten. It is overwriting the previous file. Then here, sediment yield, and then create. So previously we were seeing only the information corresponding to the reach, because there I was extracting information from the reach, but here I'm extracting the information from the subbasin, and we could see the overall variation. So say for instance, for sediment yield, we have the minimum and maximum, and then we could have the information about which subbasin has the highest sediment yield, and then based on that we can apply different management operations into it to reduce it. And then if you wanted to print it, you could just print by using the same approach. There are a lot of other options, like you could create a video, and you could also plot your, say for instance, reach output corresponding to the observed data. So I would, you guys can explore it by yourself, and if you have any other issues, just let me know. I think I'm done with my explanation. Thank you so much for your time and attention. You were really patient audience. Thank you so much.
Thank you very much, Bhumika. Excellent talk. Thank you very much for your time. I would like to request Sushant for announcement for next week, and then we will close this session. Thanks. Dr. Sushant ji.
Yeah, thank you everyone, and good morning, good afternoon. I think it's already good day. Bhumika, good morning to you. Thank you so much that you woke up so early in the morning and giving such an activated lecture. I was fully motivated.
I was a little bit worried, because from the past 7 years I'm living alone and I don't speak until 10 a.m. in the morning. I was a little bit afraid that what if I didn't have any motivation to speak, but you guys were really passionate about everything, and that also motivated me at the end. So
yeah,
I really hope that you guys are taking something at the end of this lecture.
Certainly. And for the audience, for the next week, what we will be doing is, we have already set up the model. Now, what we can do with the model, that is all we're going to do. how to read the files using R. So we will not be using QGIS anymore. So we will be using R as a software, and we will be analyzing SWOT outputs, and we will be using SWOT Cup as well. So more information will be coming out to you guys with the SWOT Cup package, which is not a licensed one. I'll share it with everyone. And yeah, one day will be completely dedicated to SWOT Cup, and one day will be completely dedicated to climate change studies and how to read the SWOT outputs and how to interpret the information coming from SWOT. If you don't have QGIS, if you don't have ArcGIS, how to read information from SWOT using R. So this is all we are going to do next week. Would appreciate if you can join and inform your colleagues. We'll be looking forward to meet you guys next weekend.
Yeah, thank you. Thank you very much, Dr. Sushant, Dr. Bhumika again, and everyone. And definitely we will coordinate the link to join next week. And for the timing, if you have any question, you can text us or you can directly text to Dr. Bhumika or Dr. Sushant. So take care for the time. Bye-bye, everyone.
Bye.